All right, so we've discussed some of the our lab setup, and now we'll actually look at PacketScan and its performance and its workings. So PacketScan is our all IP analyzer. It handles a lot of protocols, almost all protocols over IP, and it's using it can operate on 10 megabits, 100 megabits, gigabit, and also now we have a 10 gigabit PacketScan platform. So they can, some of them can operate at wire speed. The normal PacketScan can also operate off of the NIC card. Now, here we're going to show you how the essential features of PacketScan. One of the things that it can do that it's very versatile with is voice codecs. It has a variety of voice codecs, something like AMR narrowband, AMR wideband, G711, there's EVRC. Actually, the list is so large, you have to go to our website to check it out. The other thing that it has is it can actually go into the Rtp packets. Rtp is the real-time protocol, and extract the voice and give you graphical display of that voice. It can analyze tones, it can add digits, voice. It actually can store that voice and gives you a lot of insight into the actual voice stream. The other very important characteristic of PacketScan is its ability to analyze voice quality. So how does it do that? Without actually going into the RTP, you can analyze voice quality by doing something called R-factor E-model. And that is judging from the stream of the packets whether they're evenly flowing or whether they're losing packets or jittered packets. You can assess the quality. It's a very accurate way of assessing quality, and this PacketScan does that. So let's go into the actual PacketScan application, the different screens, and we'll examine each one by one. Thank you. Okay, our PacketScan analyzer, as we had said earlier, consists of two main screens. One is called our main analyzer. That's this screen. Here, we're showing all of the Ethernet frames one by one. And of course, whichever frame is highlighted is shown in detail in the second pane, where all of the contents, the protocol, the MAC layer, the IP layer, just like in Wireshark or other Ethernet analyzers, we can show the complete breakdown. Also, a third pane is where we actually collect the packets throughout the capture and collect them all together in what we call data records. So down in this third pane here, if I double click on this, now all of the packets associated with one call, that was a call from 301-838-5591 to 301-670-4791, are collected, and here you see the signaling. So this is the main feature of the main analyzer screen. It can analyze a variety of VoIP protocols like SIP, Megaco, MGCP, H323, and so on, and a variety of also protocols like SIGTRAN and SS7 type of derived protocols. It can also analyze a lot of the wireless protocols that ride on IP, like GSM, LTE, IUCS, or 3G protocols. So anything that rides on IP, this PacketScan is capable of doing it. So here, we are obviously we're generating session initiation protocol calls, SIP calls. Okay, continuing with our PacketScan analyzer, as I had said, PacketScan can collect all of the packets associated with a single call, and it can build call data records. Here I've highlighted one of the calls that is occurring within the system. And if you double click on this, all of the signaling associated with that particular call, in this case it's a SIP protocol, the invite, trying, ringing, OK, act, buy, and again the acknowledgement of the buy is all collected, and the timestamps are provided, and so you can actually see the entire protocol as it took place. If the call was incomplete, you'd see perhaps some of the incomplete packets that are missing in the signaling. The other aspect of PacketScan is the PDA. The PDA is actually going into the content of the packets, the Rtp, and is going to display those contents and operate on those contents. Here we're seeing that it has about, here this is the collection of all of the calls, and showing that there are about 50 calls up and running. And as time progresses, calls are obviously being initiated and terminated. And in this case, as I had mentioned earlier, we've got about 60-second to 120-second duration calls. And now, up at the top of the screen, we have the calls as they are progressing, each and every call. And we can see here that we have lots and lots of calls that are being accumulated. If we highlight on any of these calls, like for example this. Okay, so now we are looking at the PDA, Packet Data Analyzer, and the main purpose of PDA is to look into the contents of the Rtp packets, collect all of the contents, and show the contents in terms of voice quality, jitter, packet loss, and so on. So here we're going to show you that since we're generating calls in AMR wideband, AMR narrowband, and G711, let me highlight the AMR wideband call. So the one highlighted here is the AMR wideband call. It's 16,000 samples per second, and if you can see here, these are the number of packets. An important column here is the conversational score, MOS score, and the listening MOS score. So both of these are indicative of the voice quality of that particular codec. Since we have no packets discarded and no missing packets, that is the best that can be expected from AMR wideband 4.18. As you know, the MOS score can go from 0 to 5, and 4 being quite good. Now let's take a look at a G711 call. This is PCM A-law and 8,000 samples per second. This is what our conventional telephone network handles, A-law and mu-law. But you can also send A-law, mu-law traffic over the packet network. And in this case, we can see here that if you're sending A-law, you're getting a MOS score of about 4.2, which is almost equal to the GSM wideband, the AMR wideband protocol, even though the AMR wideband uses substantially less bandwidth. I think AMR wideband here is using about 20 kilobits per second, whereas A-law at 8,000 samples per second is using 64,000 bits per second. And along with the Rtp overhead, you actually it's quite a bit larger. So the AMR wideband is a very popular protocol, voice codec that gives you excellent voice quality and very, very reduced bandwidth. So also AMR narrowband is used, and here's a call that is AMR narrowband. It's 8,000 samples per second. Its quality score is about 3.65, which is still quite good. Now, other statistics that the PDA provides is packets discarded, missing packets, duplicate packets, out of sequence packets, average gap between. As we were saying, the PDA screen provides you aggregate statistics of all of the calls that are being collected. And as you can see here, there are actually hundreds of calls that we have captured, and any one of those calls can be examined in detail. But this screen is the aggregate screen, and it gives you statistics for all of the calls that have been collected so far. So let's take a look at what these aggregate statistics are. First of all, the main screen here is the number of active calls. And you can see here that there's been as high as 54 calls or as low as 41. So this gives you a number of active calls as a function of time. Also, some aggregate statistics that are important for packet voice transmission is average jitter distribution. Average jitter distribution, of course, is very, very important because packet networks can introduce a jitter, which is almost the most deleterious impairment that you can introduce to packets. Packets don't flow smoothly. They're actually, they arrive at the receiver in spurts sometimes. So, but here, since we have a okay, as I said, the PDA, main aspect of PDA is to analyze calls. It provides aggregate statistics on all of the calls collected, as well as individual call statistics, individual information on the individual call. Here on this main screen, we're seeing the aggregate statistics. This graph here is the active number of calls, and you can see here that there's been about 54, a peak of 54 calls, and a trough of about 40 calls. So the number of calls is fluctuating, but it gives you this number of active calls as a function of time. The other thing that's very important for packet networks is how these calls are experiencing jitter, and how much jitter are they experiencing in total. So here is a graph of the average jitter distribution. The average jitter distribution is an important statistic because it tells you over time how much jitter all of these packets are experiencing. In this case, we have a pretty clean connection because it's in the lab, and the IP cloud impairment has been basically set to 0. So we have almost no jitter on all the packets. Looks like here, since we started PacketScan, about 1,700 packets have transpired. I just recently restarted it. And all of them are experiencing almost no jitter. The next aggregate statistics is the E model. And this is a very good statistic that gives you the overall quality of all of the calls that have transpired so far. And you can see here that over 81 calls had a very high score. I'm sorry, the R factor was 81 for about a number of sessions, over 950 calls experiencing very high quality score. That's called the R factor, but let's go to the MOS score, MOS. So you can see here, above 4.1, there was about 950 calls above 4.1. There were some calls, some of those were the, some calls that maybe have had some packet loss. There were a few calls, about 50 calls, that had a MOS of 3.7 to 4.0. And probably the narrowband, AMR narrowband calls experienced a voice quality between 2.7 and 3.6. So that was about 700 calls. So we had a mixture of calls going on, AMR wideband, narrowband, and G711A loss. So this gives you at a glance how many calls, how many are poor calls, how many are excellent calls. So a very good graph to give you a quick sense of what's happening with your network. RTP PacketScan. Here's another chart that gives you as a function of out of order packets, missing packets, duplicate packets. So here we're seeing total number of audio packets and what fraction were out of ordered and duplicate packets. As I had said earlier, the PDA is used for analyzing voice band information, including voice calls of different codec types and fax calls, like for example T30 and T38, as well as modem calls and also video calls. So all of those types of traffic can ride on RTP, and this will give you at a glance how many are out of order, duplicate, and so on, and lost packets. So in this case, we're not having any missing packets whatsoever. Here is the call graph. The one highlighted call is given, is displayed in its all of its signaling. So you can highlight invite, and if you do that, here is the actual invite packet in all of its detail. The trying packet, for example, would be giving you there. Now, Right now I have actually the packet analyzer running, so I should really stop the packet analyzer when I'm doing this type of analysis. So let me do that. Let me stop the analyzer and then go back to this graph, and now I shouldn't have any issues bringing up different packet contents. Ringing, okay. So that particular call that is highlighted can be looked at in greater detail with its signaling packets and so on. This ladder diagram, very useful for packets that perhaps were problem calls. If you wanted to go into a particular call and give you a detailed analysis of what's inside a particular call, inside the RTP, we have another view. It's called a call detail view. Click on that. This particular call is analyzed on a packet-by-packet basis. So for this particular call, it's AMR. Every 20 milliseconds, a packet is transmitted. Right. So those are the DTMF digits, and it looks like we can actually send DTMF digits in narrowband AMR. It's able to decode some of the digits here. So all of the packets for the entire duration of the call is provided here, one packet at a time. And the statistics associated with that packet are also provided, for example, gap, delay, and so on, and jitter. So if there happen to be any digits, DTMF digits, or tones, or whatever, they would be given here in the in-band events. This particular call had a MOS score for its entire duration of about 3.6. So this is the MOS duration. So if there was a glitch during the actual call, you would see it on this graph. RTP events, these would be typical RTP events. There aren't any in this particular graph. The actual call can be shown in wave format meaning analog, and we can show them in a mode where they're the east and the west, and you can actually play this as well, play the audio, and this gives you the entire, you can actually expand it to show the entire call, or you can magnify it to show specific sections of the call. So that's very useful. The spectral display is also available, but this will normally only run during when the call is actually active. Some of the other voice quality statistics are given in this tab. These are this particular call had pretty good quality, so you don't see much variation in the R factor. R factor is one of the statistics that is relevant to voice quality. Other degradation factor, burst metrics, jitter, buffer statistics. So in another video, we'll actually go into each and every one of these statistics and explain to you what they mean in detail. But now, just to give you a flavor for all of these statistics. So Rtcp is another packet that is exchanged between the endpoints to provide quality information to each endpoint. And so that's also provided. In this case, there were four packets, four Rtcp packets exchanged between the endpoints, providing information such as jitter and delay and so on. Gap distribution. This particular call had this type of gap distribution. Meaning, gap is essentially a form of jitter. So that's the at the end of that. Okay.